Let me start with an introduction to Dora hacks. Dora Dōjō is an open source knowledge community focused on cutting-edge technologies such as encryption, Web3, and the whole community is built by hackers. Dora Dōjō regularly organizes knowledge sharing sessions with the live broadcasts like the one you're watching right now, audio and text. And it covers a wide variety of topics, including L1, L2 blockchains and their consensus algorithms, architecture, and very much all of the related content, including the latest blockchains, encryption methods, zero-knowledge proofs, hash functions, distributed systems, and various protocol stacks. So I encourage everyone to look at the bounties and pick the ones that you feel comfortable and interested in, and do your docs to share and win the bounty. Share the knowledge and win the bounties. So for today, we're gonna have a workshop. Let me share my screen on the following topic. We're gonna discuss digital signatures, and more specifically, we're gonna talk about KZG polynomial commitments, their properties and their applications in ZK SNARKs. KZG polynomial commitments is probably one of the most widely used building blocks in modern ZK SNARKs. So just to quickly introduce myself, my name is Alexei, and I'm a staff engineer at one of the blockchain companies. And this talk is specifically for Hacker Dōjō workshop on the bounty, on the one of the bounties I showed you just before the slides. So what are we gonna look at today? At first, we're gonna review the polynomial commitments. We're gonna talk about what are the commitments and what are the functional commitments, and more specifically, what are polynomial commitments. Then we're gonna have a small math review. We're gonna look at the important building blocks we need to have in order to understand how KZG polynomial commitment scheme works. Now we're going to discuss certain properties of these polynomial commitment schemes, its variants, and finally I'm going to mention the applications that are probably one of the most known applications of KZG. Yeah, so let's begin. First of all, we're going to look at what is a commitment scheme. Generally speaking, a commitment scheme is two algorithms. The first one we're going to call commit, and it takes a message M and a certain random value R, and produces a commitment string, which is a byte string, and this byte string can be publicly shared. A message, though, is only known to the committer, to the person or the entity who produces the commitment. Later, when committer reveals M, anyone can verify that the commitment was made specifically for this message. So committer reveals M, and it also reveals an R. And there is an algorithm, which we're going to call Verify, that takes as an input the message, the commitment string, and the random value R. And the output of this algorithm is either accept or reject. So again, this scheme basically allows someone commit to a certain message in advance without disclosing the message, and then prove that this was the actual message we committed to. One of the examples, one of the practical examples of such commitment is an auction with the hidden bids. So if I bid a certain amount of money for a certain object that's being sold, I probably don't want to reveal my bid beforehand, and if I have the winning bid, I can reveal it later on. So commitment schemes have two important properties. First one is called binding. Binding tells us that committer cannot produce commitment for two valid openings. So for two valid pairs of M, message M, and a random value R. And the second property is hiding. Knowing the commitment, which again, the commitment string is publicly available to everyone. No one can deduce anything about either message or the random component. So usually, specifically for hiding property, we need to include this random value, because otherwise we risk disclosing information, especially if the message space is not large. So let's say the message space consists of integers from 1 to 1 million, and it's easy to just iterate through the set of numbers, this set of numbers, and to check which number gives us the specific commitment string. In order to avoid this, we pair the message with a certain random value, and usually this is how, in most schemes, we achieve the hiding property. Okay, so the easiest example of the commitment scheme is so-called hash commitment. By hash commitment, in hash commitments, we fix a certain suitable hash function. Usually it's a cryptographically secure hash function, which is collision resistant, pre-image and second pre-image attack resistant. And when we commit to a certain message, we just hash the message and a random value to achieve hiding. So because it's a hash function and it's computationally infeasible to reverse it, the commitment itself doesn't reveal any information about the message M. When we disclose the message M and we disclose the random value R, anyone with the commitment string can check that indeed the hash of the message M and the random value R equals to the commitment string, and thus verify our commitment. So again, if we choose H correctly as a hash function, we achieve both hiding and binding properties for the hash commitment. Next, we're going to look at the important and more relevant example, class, let's say, not an example, a class of commitments called functional commitment schemes. So the difference is that rather than committing to a certain message, we commit to a function, and we want to be able to reveal this function at just the certain points. So how does it work? We first of all choose a function family, capital F, which consists of function taking the input values from the set X and mapping them to the set Y. So a committer, or we can also call it a prover, since in ZK SNARKs where these commitment schemes are often used, we just call them provers, picks such F from a function from this family and picks a random value R. It builds the commitment and sends the commitment to the verifier. So at this point, we commit to a certain function in the predefined family capital F. And committer or prover cannot change this function to something else later on when the verifier tries to evaluate this function. So we can say open this function at a certain point x. So later on, the verifier can ask the prover to evaluate f of x. And the prover returns y from the capital Y, from this side of the image of the function, and along with the y, it returns the proof pi. So the proof pi should prove to the verifier that f of x is indeed equals y, and that f belongs to this family of the functions. And the verifier can either accept or reject the evaluation of the function f. So that's the basic idea of the functional commitment schemes. Now let's take a look at the specific definition and specific components of the functional commitment schemes. So first of all, as we've just seen, we need to define a certain family of functions with which we're going to work. So that's the first step. Next, we need to usually have a certain setup procedure. So what does it do? Setup procedure produces global public parameters. We're going to call them GP, and takes as an input usually a so-called security parameter. So security parameter here in this presentation, we're not going to discuss it thoroughly, but you can think of as the number of bits that affect the cryptographic security of the commitment scheme. So if we look at the encryption, for instance, symmetric encryption algorithm like AES 256, so this like 256 is exactly like the security parameter. So it says that the space in which we operate has 256 bits, the keys, the private keys, and in case we want to brute force the private key and try to break the encryption scheme, that would be the security, the complexity of the security algorithm that we need to overcome. Yeah, basically. So the important thing again is that global parameters are available for everyone, and the procedure is just executed once. Next, we definitely going to need to have a commitment function. The commitment function will take as an input global parameters, this function f, and a certain random value r, and produce the commitment. Next, because this is a functional commitment scheme, and we want to be able to not just disclose the whole polynomial, the whole function f, but we want to be able to disclose it at a certain point and evaluate it and prove these valuations, we need to have the prover and the verifier algorithms. So how do they work? Basically, we have the commitment. We have the x and the y. So the x is the input to the function. The y is the result of the execution of the function. Proof. Proof is executed. Proof algorithm is executed by the committer or the prover. On the diagram that we've just seen, it's on the left side. Yeah. And the prover takes general global parameters, the function, the input and the output of the function, and the random value r to produce a short proof. So the key idea here is that we want the proofs to be short. We're gonna now see what do we mean by this. And when we need to verify the evaluation, we take the global parameters, we take the commitment that was produced by the commit function, we take the input and output, supposed input and output that we want to verify, and we take the pi as the proof. And we either accept or reject. So it's important to understand that functional commitment schemes are itself SNARKs. And if we use these random R to hide information, then we will actually get ZK SNARKs. For the following statements. So the proof pi is actually verifying and proving the following, that first of all, f of x equals y, then f belongs to the family capital F, and that the commitment that we previously had received from the prover actually holds. Yeah, so that's the valid commitment. Okay, let's take a look at some examples of important functional commitments. First of all, polynomial commitments. In the polynomial commitments, we commit to univariate polynomial as our functions. So the family of the functions that we take are polynomials over the finite field Fp, and the polynomials are of the degree at most d. And they are univariate, so they take just one input. This is the type of commitment we're going to look at today closely, and KZG is exactly like the polynomial commitment. Next, we're going to have multilinear commitments. They allow us to commit to multilinear polynomials. So multilinear polynomials are polynomials of several variables. So for instance, f of x1 to xk. But the degree of each term in the polynomial is at most 1. So that means that, for instance, we can have a polynomial x1 multiplied by x2 plus x1 multiplied by x3, x4 plus x5. But we can't really have, for instance, x5 squared, let's say. That would make it a general polynomial, not a multilinear one. And finally, one more important commitment that is often used in SNARKs is the vector commitment. You can think of it as the commitment using Merkle trees. So instead of committing to a function, we commit to a vector, and we want to be able to open this vector at a certain index. So this is a specific instance of the functional commitments where functions are just the vectors, and functions are returning the elements of the vector by the indices that we provide. But again, for today's talk, we're gonna closely look at the polynomial commitments because KZG falls into this category. So let's look at how we define and how we construct polynomial commitments. So let's recall that prover commits to polynomial of a degree at most d over the field of the finite field Fp. So for us to have a functional commitment and specifically polynomial commitment, we need to have an evaluation protocol. So an evaluation protocol for us is the protocol that allows us to prove that the committed polynomial indeed satisfies a certain relation. So we take the polynomial at the point u and we get v as the output, and that the degree of the polynomial is less than d. So the verifier in our case knows the degree, knows the commitment, and knows the input and output values. And to restrict the size of the proofs, and the verification time, we want them to be bounded by logarithm of the degree, of the polynomial degree. This complexity can also depend on the security parameter lambda, but the most important part is that we want to make sure that neither the proof size nor the verification time requires more operation than the logarithm of the degree of the polynomial. So a few real-life example of polynomial commitment schemes. So obviously, the one that we're going to look at today is the bilinear group-based commitment scheme, KZG. It's one of the most widely used, and the only significant drawback it has is that it requires trusted setup. We're going to look and discuss it shortly. But it's one of the most time and space efficient commitment schemes. There are commitment schemes that rely solely on the hash function. So, for instance, the so-called FRI scheme. The drawback of this scheme is that it produces longer proofs, usually at 100 kilobytes per proof. There are commitment schemes that use just elliptic curves, not the bilinear groups, which are a more complex and more restrictive set of, let's say, building blocks that we can use. So one of the most well-known schemes is so-called bulletproofs. The drawback of the bulletproofs has the linear verification time. Again, let me remind you that we would love to have the verification time bounded by the logarithm of the polynomial degree d. And linear verification time is basically violating this constraint. Let's look at first of all at the very simple, trivial polynomial commitment scheme. So let's say that we have a polynomial with coefficients a sub I. And in this case, one might want to commit to a polynomial by just taking this suitable hash function and applying it to the set of coefficients, to the tuple of the coefficients, and some random value r to achieve hiding. So indeed, this would commit us to the polynomial, because if we change any of the coefficients, the commitment will be broken. In this case, the evaluation protocol would look like this. The prover sends pi, which is the set of all the coefficients and the random value r to the verifier. So in a nutshell, we are sending the whole polynomial to the verifier and the random r. And the verifier checks, because the verifier has all the coefficients, it can just compute f of u, checks that it equals v, and also check the hash function and verify that the commitment holds. So yeah, it looks good, but it has two problems. First of all, we disclose the whole polynomial. So in this scheme, we need to send all the coefficients, and instead of just proving that the polynomial has a certain value at a certain point, we just give away the whole polynomial. The second problem is the proof size and the verification time. Because we send all the coefficients, we basically send d coefficients to the verifier, and it means that the proof size is linear in the degree of the polynomial. And because the verifier has to actually compute the polynomial, this would give us the linear verification time for the verifier. So that's why the trivial polynomial commitment doesn't really have the properties we are looking for. So before we look at how KZG works and why is it so efficient, we need to recall and review certain basic mathematical concepts that are often used in cryptography. First of all, we need to recall that what are the groups. A set G and a certain operation star with certain properties is called a group. So it's much easier to look at groups as an example of integers. So integers and the operation addition. So instead of the operation star, the abstract operation, we take the specific one addition, forms a group. And the properties any group should adhere to are the following. First of all, the group should be closed with respect to the operation. So if we have two elements, A and B, that belong to the group, A star B, so in our case it will be A plus B, must also belong to the group. Well, it's easy to see for the integers. If we sum two numbers from the set of all integers, we're going to get another integer. So 1 plus 2 equals 3, and 3 is an integer. So 3 belongs to the set, to the group G. Associativity. If we have three elements, A, B, C, all belonging to group G, and we apply our star operation to A and B first and then to C, it's the same as applying star operation to B and C and then applying the result to A. Again, it's very easy to see with addition. A plus B plus C is the same as A plus B plus C in the brackets. And the result also belongs to the group G due to the closure property that we discussed. Identity. So the third property tells us that there should be a unique element belonging to G, such that for every every other element in the G, E star A equals A star E and equals A. So for the integers, this and the addition, this unique element is obviously 0. So if we add 0 to A, that's the same as adding A to 0, and the result is just A. Inverse. So there must be an inverse for each element. So if there is an element A, there must be an element G in the group such that A star B equals B star A and equals E. The inverse is, again, very simple to grasp. The concept of inverse is just the negative counterpart of any number. So if A is 2, B should be minus 2. Then 2 plus minus 2 equals minus 2 plus 2 and equals E, which we have just seen are basically 0. So in cryptography, usually we use different groups, not just integers, and one of the most commonly used group is the group of positive integers modulus P under the multiplication. So we take as a star operation multiplication, and we perform all the multiplications by taking the remainder of the division, integer division by P. So that's what we call modulus P. Another common example is elliptic curve groups, which are ubiquitous in cryptography as well. So now we know what are the groups, and we need one more component, which is the group generator. So a certain element G is called a generator for the group if we can build all other elements in the group by just taking all the powers of G. So by saying taking powers, we mean consecutively applying the group operation. So you can think of it as a repeating multiplication or repeating addition. Let's take a look at the example. So this is a finite group modulo 7. Basically, it consists of all the remainders when we divide integers by 7. And these remainders are 1, 2, 3, 4, 5, 6. And then if we look at 3, we're going to see that 3 to the power of 1, 3 to the power of 2, 3 to the power of 3, and up to 6, they're going to give us all the elements. So 3, 2, 6, 4, 5, 1. All the elements of this group. So that's why 3 is the generator for the group. Okay, so next, taking this into account, we can represent a group as the powers of the generator G. So we just need to know the generator and the consecutive powers. They basically give us the full representation of a group. If we look at a group this way, we can think of a question. What if we want to take logarithms of the group elements? So what does it mean? If we are given an element of the group Y, can we find such x that g to the power of x equals y? This is a well-formed problem because all the elements of the groups can be represented in such a way. We've just seen that the group is just the set of powers of G. Yeah, now we need to be able to, we want to find the power that we need to take G2 to get Y. This problem is called a discrete log problem. So we all know the logarithms from the high school, but this one is different because we operate in a discrete setting. So we have a discrete number of elements, not the continuous real numbers, but just p elements in the group. And connected to the problem of finding a discrete log, there is a well-known and highly used in cryptography assumption that discrete log is a computationally hard problem. So by computationally hard, we mean that there is no good algorithm that's gonna give us X. And roughly speaking, we have to resort to just looking through all the possible values of X to find the one that we need. Again, in contrast with the usual log that we all have done at least once, the usual logarithm is easy, is not computationally hard, and in real numbers it works just fine. But the discrete log is different. And let's take a look at the example. So let's say we need to find x, such as 3 to the power of x equals 4 modulo 7. And it's not clear how do we even approach this. On the previous slide, we've seen that 3 to the power of 4 is actually 4 modulo 7. And yeah, one can verify this by raising 3 to the power of 4, which is 81, and taking the remainder when dividing by 7. So we can just do this and see that it's actually 4. Yeah, but the trick is that there is no good algorithm, and we probably have to just look through all possible x to find the right one. There are faster algorithms, but if the size of the group is large, and usually P is somehow comparable to 2 to the power of 256, which is more than the number of atoms in the observable universe. This problem is still computationally infeasible on regular computers. Though it must be noted that when quantum computers will arrive, this discrete log assumption probably will not hold anymore, because they can do this in polynomial time, not the exponential time. But for now, we can assume that no one can do this efficiently enough, and that would be the important building block for the KZG polynomial commitment. We're going to need one more computational assumption, one more problem that is computationally hard. It's called Computational DiffieHellman assumption. It's a bit more restrictive, so it's a stronger assumption. And it tells us that if we are given a group and we have the generator and g to the power of x, g to the power of y, knowing this, we can't really efficiently compute g to the power of xy. Yeah, so if we could solve discrete log problem, we could have been we could find g to the power of xy by just taking the discrete log of g to the power of x and g to the power of y. Basically, we're going to know x and y, and we're going to multiply them and raise g to the power of the product. But discrete log is tough, as we just discussed, and we can't really do this. So again, discrete log is a more general assumption, and DiffieHellman is a stronger one. But it's widely believed to hold and to be sufficient for many cryptographic constructions. And the final element that we're going to need is so-called bilinear pairing. So to define bilinear pairing, we're going to need two groups. So the group of the order of P, G, is generator, the target group, and we're going to need the pairing operation E. So G can be thought of this source group. So this is the group on which the operation E, this bilinear pairing, works. It has the order of P and the generator G. G sub T is a multiplicative group of the order P, target group. We don't need to know the generator. We just need it. It can be different. Doesn't have to be the same. But that's the group that the results of E will belong to. And finally, the pairing itself. Pairing is an operation that takes two elements from G and produces an element in GT, such that it respects the exponentiation. What do I mean by this? If we take E of P to the power of x and Q to the power of y, it's going to be the same as taking E of P and Q and raising the result to the power of xy. So how can this be used? Basically, by just knowing g to the power of x and g to the power of y, we can check that some h, some other element h, equals to the g to the power of xy without knowing x and y. By just applying bilinear pairing to gx, gy, and applying it to the h, to the element h, and comparing the results. Okay, so now we can take a look at one example of a digital signature that used this bilinear pairing to get a better understanding of how it works. So let's say we have this bilinear pairing setup. Again, two groups, generator and the operation E. So Someone wants to sign a private message, just a message. Sign a message for others to verify the authenticity of the message. We're going to have a private key, x, and a public key, which is g to the power of x. Again, due to the discrete lock assumption, by disclosing g to the power of x, no one can actually take the logarithm and find x. Yeah, so this value can serve as a public key without compromising the private key. The signing of the message happens as follows. So we find the cryptographic hash of the message that we want to sign and raise it to the power of x. Again, we need to have the cryptographic function from the space of all messages to the G, to the source group, so we can actually raise it to the power of x. So our signature would be h of m to the power of x. That's the signature. Now, when we want to verify this signature, anyone can check that the hash of the message and the public key under the pairing operation equals to the signature and the generator under the same pairing operation. So if this holds, that means that the signature is valid. So the verifier knows the signature, the verifier knows the message and needs to verify the authenticity of the message, that it comes from the person who signed it. And in order to do so, it just requires to execute two pairing operations. Okay, this is so-called BLS signature, which is a nice application of bilinear pairing. Finally, we can start with the actual KZG setup. So how can we use all this to build a commitment scheme for polynomials? Again, we take a bilinear pairing. We take a family of univariate polynomials of degree up to d, and we need to start with the setup procedure. So we take the family, we take the security parameter, and we produce the global parameters for the KZG algorithm. How do they do this? We sample a random tau from the field over which the polynomials are calculated. And as the global parameters, we take g to all the consecutive powers of tau up to d. So g to the power of tau, g to the power of tau squared, up to g to the power of tau to d. Again, these global parameters are known to anyone, but no one actually can compute tau from them. So tau is a secret that has to be discarded. So the important and the major problem with the KZG commitment scheme is that it requires trust into the fact that the entity who built the global parameters has actually discarded tau. There is no way otherwise the tau can be recovered from the global parameters, but it's important to understand that this requires a certain level of trust. Other polynomial commitment schemes, FRI, bulletproof, do not require a trusted setup. Okay, so that's the setup phase. How do we commit? So prover knows the global parameters. They are known to everyone. And it constructs the commitment in the following way. So we take the polynomial of the degree up to d, and we calculate the commitment as g to the power of f of tau. Now the trick is that we don't actually know tau. No one knows it. It has been properly discarded. And that's why direct calculation of f of tau is not possible. But due to the exponentiation rules, we can find what g of f of tau is without actually calculating f of tau. So we expand f of tau by substituting the tau instead of x. So we get g to the power of f0 plus f1 tau plus f2 tau squared and up to fd tau to the power of d. And then by using the regular school math level exponentiation rules, we can isolate each term here in the sum in the power and make it a separate exponent. So we take g to the power of 0, g to the power of f1 tau, g to the power of tau squared f2, and so on. And by rewriting it slightly, we see that we actually look at the global parameters. This is exactly the global parameters that we have, raised to the powers that are just the coefficients of the polynomial f of x. That means that all we need is to raise the global parameters to the power of the coefficients, and we have our commitment. So again, the prover can compute the commitment without knowing tau. The size of the commitment is only one element, which is perfect. It doesn't depend on d. So after we compute it, we have just one element, one number, and that's it. That's something that we want. Okay, so how do we generate a proof then? So recall that we need to open our polynomial at a certain point u and show that it actually prove that it actually equals v. Because f of u equals v, it's clear that u must be the root of the polynomial f of x minus f of v. Again, it's pretty much obvious. If we substitute u instead of x, we're gonna get 0. So u is the root. Because u is a root of this polynomial must be divisible by x minus u. So it means that f of x minus f of u can be represented as x minus u multiplied by the quotient qx. No reminder. So what a prover does, the prover computes q of x and builds a proof by computing g to the power of q of tau. Again, the way it is done is similar to the way we calculated g to the power of f of tau. We don't need to know tau to be able to compute this. Knowing the global parameters is sufficient. Now, how do we verify it? So verifier receives the commitment, verifier receives the proof, and the supposed evaluation of the polynomial at the point u. And the verifier needs to check that this polynomial equation holds. First, it exponentiates the expression. So it basically raises the left and the right side to the uses the left and the right side and raises g to these corresponding powers. There is a small typo. There should be g to the power of x minus u qx. So it's not multiplication. It's right up here. So basically, when we do this, all we want is to check that this holds for x equals tau. So again, we exponentiated this expression and we substitute x for tau. Now we can compute g to the power of tau minus u because we know g to the power of tau from global parameters and we know u is public. It's number that we've chosen as a verifier. And we know g to the power of q tau. That's the proof that was sent to us. But the problem is that while we know these two components, we can't really figure out the g to the power of tau minus u to the power of q tau. Due to the computational DiffieHellman assumption. This is the second assumption that we looked at. However, pairing is going to help us. If we apply pairing to both of the sides, so this is something that we need to check. We apply pairing to both sides and use the pairing rule. We can take the powers out of the pairing operation, and if the pairing on the left and the pairing of the right is equal, this means that the exponents are equal. And in the powers, in the exponents, we have the exactly the equation that we want to check, this one. Yeah, so that's the original goal that we had. We need to verify that f of x minus f of u equals x minus u times qx. So these exponents will match only if the pairing holds. The left and the right value coincide. Okay, so the question is, why is it enough to check this polynomial expression and equality just at one point? In fact, we want to make sure that it holds for every x, but we just check it at 1 point tau. And there is a nice little observation which is very important, and most of the cryptography behind SNARKs are to some extent relying on this observation. Though, if we have a non-zero polynomial and we pick a random r, the probability that this polynomial will be zero, will equal zero at this point, is less than the degree of the polynomial divided by the p, by the order of the field. So how do we arrive at this? One of the basic facts in algebra, if we have a non-zero polynomial of degree d, it should have at most, d roots. So this is the number of roots, and all possible values, the size of the field is p. So we pick one of them, d of roots, over all possible outcomes p. So that's why the probability is d over p. Yeah. So again, d roots, p, all possible values. And the next thing that we need to see is that if p is a large prime, and usually again in cryptography we deal with the large primes of the order of 2 to the power of 256, for instance, then dp will be close to zero. P is usually very large, and d is pretty limited. Like rarely we have very large polynomials of the very high degrees. So for us, it means that if we pick a random value r, and it actually is such that f of r is zero, then with a very high probability, f is a zero polynomial. So the probability that we just guess the root of the polynomial is extremely small. So if we indeed randomly guess the root, it means that this polynomial is probably zero everywhere. So this is a simple test for the zero polynomial. Now we can use this test to build an equality test. Again, our question was, why do we check at just 1 point to make sure that this expression holds? And yeah, we can build an equality test. We can consider the difference between two polynomials, and if we pick a random r such that this difference is zero, it means that this polynomial the difference is 0 everywhere. But this in turn means that these polynomials are equal. So again, by just picking one random number and checking two polynomials of this random number and seeing that they coincide at this random number, this random element R, would with very high probability mean that these polynomials are equal. So that's why, instead of checking like general equation with the variable x, we can just check it at one point tau. And tau serves as a good random number for us. It's not actually random, but it's actually random. Remember, like we don't pick it randomly each and every time, but on the setup phase, let's recall, we had a setup phase. We picked it at random here. And it is not known for everyone, to anyone, so it's like it was discarded. And that's why it's a good point to use where we want to have this equality test. Okay, so this is again the overview of the KZG. We have the setup. We commit with raising the generator to the power of f of tau. Send the commitment to verifier. Verifier challenges us with the u. We find the q of x and send the proof, which is the quotient of tau, and we raise the generator to this power. And we send it along the value. And the verifier checks just one pairing operation, which is very computationally efficient. Just one operation, doesn't depend on the degree of the polynomial, and the proof size is also constant. So let's quickly look at another important aspect that we need to take into account. So how can we make sure that the prover actually knows such f that the commitment of f equals this g to the power of f tau? It might happen that the prover just took some random value instead of calculating f of tau and raised g to this power. And that actually makes the whole protocol of the KZG polynomial commitment not knowledge sound. So we are not confident that there is a knowledge of the polynomial on the side of the verifier. There is a nice little trick that is frequently used in different constructions by adding by using the linearity of the pairing operation. We can make sure that there was an actual computation of the polynomial. So to achieve this, we get one more secret a and expand the global parameters with g to the power of a up to g to the power of to the t tau to the power of d. So basically, we have another set of global parameters, which is derived from the original set that we discussed by just raising to the power of alpha. Now we ask the prover to generate two commitments. One commitment is g to the power of f tau, and the second one is raised to the power of alpha additionally. It's important to know that there is one-to-one correspondence between these two commitments. So they are, neither of these commitments can be changed without affecting the other one. Yeah, so they are linked. And because the prover doesn't know alpha, that's the secret that was discarded during the setup phase, and cannot compute f of tau, the only way to compute g alpha f of tau is to use the actual polynomial f of tau. So you remember how we did it without alpha? The same way we do it right now, but just multiplying the whole polynomial by alpha. So in this way, the verifier can be sure that the prover does not cheat and does not use some random value instead of just real polynomial f of tau. And this polynomial must be the same both here and here, because the verifier can check the pairing and make sure that there is indeed such f that the commitment was generated for. The downside of this scheme is that the knowledge of exponent is what we just basically implemented, this called knowledge of exponent, increases commitment size. So we have more global parameters, we need to send another commitment, which is not desirable. There is a better way called generic group model. We're not going to discuss this. I'll leave you a reference to the graduate course in applied cryptography by Dan Banet in Victor's shop. Basically, the idea is that we restrict the prover to computing only linear combinations of the global parameters. So we don't allow the prover to perform arbitrary computations with G, only linear combinations. That makes it impossible to avoid using the polynomial f and just substituting it with some random value. Okay. So let's look again at the KZG and its properties. The worst thing that KZG, the worst property that the KZG has is that it requires trusted setup. But at the same time, it has very nice time and size efficiency. So commitment takes just linear number of group exponentiations, and the size of the commitment is just one number, one field element. The evaluation takes again the linear number of exponentiations, which is fine because we need to evaluate the polynomial. We need to have the iterations at least, at most. And the quotient can be computed using long division in linear time, which is also acceptable. And proof and verification, usually the most important things in any SNARK, are very compact. One field element, one pairing operation. Can be done in a very resource-constrained environment, such as blockchain smart contracts, for instance. Yeah, so the only drawback is the trusted setup. And trusted setup can be made less trusted and more trustless by so-called ceremony. So ceremony is a multi-party computation such that several parties construct global parameters. And no one can reconstruct the secret if at least one of the participants is honest. So imagine if you, in real life cases, like thousands of people participate from all over the world. They destroy the laptops they use to calculate the secrets, and they do all kind of take all kind of measures to avoid leaking the secrets. And if at least one of the participants is honest and succeeds in discarding the secret, then the ceremony is successful and nobody can ever recover the secret. So the algorithm is very simple. Each new participant samples a secret, his own secret, and raises global parameters to this power. And thus, the secret tau becomes tau s, the product. The only thing is that we need to check that each update, and these updates, again, there can be thousands of such updates, is correct. So two things have to be proven. That the contributor actually knows S, so that, again, because no one can recover S, it might happen that a malicious contributor just builds a completely new set of global parameters, and this way ruins the whole ceremony. And the final thing is that this new set of parameters, we need to check that it's actually consists of consecutive powers. So that the parameter s is known and that the powers are consecutive. Okay, so that's the ceremony. A few variants of the KZG. First of all, it's highly desirable sometimes to open polynomial at multiple points at once. And there is a nice way to do this by building another function f of x, h of x, and making sure that h of x coincides with the values of the original function f at all the points we want f to be evaluated. So we have points u1 to um, and we want to make sure that h of x equals to f of u of x. Then we construct similar quotient expression, and we build a proof on proof pi based on this equation. Use pairing to check the verifier can use this similar kind of pairing to check that the polynomial has been correctly revealed at these points. So another important variant is so-called multivariate KZG. So beforehand, we just talked about like the univariate case where the polynomial f had just one variable. Now we have x variables, can have k variables. And in this case, we kind of do similar things, but we need to sample global parameters differently in this case to have not just one, but k different taus for one for each variables. So this is more computationally involved scheme, but it allows to extend KZG to the case of the multivariate polynomials. Yeah, we're probably not going to look close at the proof of the verification. The important thing, again, that it's slightly more computationally and size intensive. So it requires logarithm proof size and verification time, where the logarithm is taken of the size of the polynomial. Let's recall that the univariate KZG, you have just O of 1, big O of 1 verification and the time, and the size. Yes, so basically you have constant time and constant size. Here, it's not the case anymore. Some practical applications of KZG. So KZG commitment scheme is used in many places, but probably like the most well-known application is the Plonk ZK SNARK, which has a universal trusted setup. Universal trusted setup means that the SNARK can have just one trusted setup and used for different computations. So again, KZG requires trusted setup, but trusted setup for a high enough high degree polynomial can be applied to different polynomials, different problems, so you don't need to perform another trusted setup in this case. So it very much suits the needs of the Plonk SNARK. Blockchains are often using KZG as the polynomial commitment scheme, again, due to its high efficiency and in the resource-constrained environment of the blockchains, it's very important to be able to save the gas costs. So, for instance, Ethereum plans to use KZG in a new transaction type for the large data blobs. So these transactions are important because they will allow Ethereum to scale. And instead of the submitting actual data to the blockchain, the transaction will carry the polynomials, and the data will be represented as polynomials, and the transactions will carry the commitments, KZG commitments to these polynomials. One of the layer 2 blockchains on Ethereum also uses KZG for the computations. So again, ZK EVM layer 2, the Ethereum virtual machine layer 2 blockchains rely heavily on, in many cases, on KZG to represent the computation and check the validity by checking that polynomial satisfies certain constraints at certain points. So KZG is actually the scheme that, first of all, is efficient, second of all, is quite straightforward to understand the basics of, and that's why it's widely used in practice. Much of the material of this lecture is derived from the Zero Knowledge Proof course, which is available at zk-learning.org, which I highly recommend for everyone who is interested in this topic to look at. On the practical side, I recommend looking at some challenges and some problems with KZG. And one of the nice problems that has been recently used on the Inganyama ZK CTF challenge was related to batch opening of the KZG commitments. So I leave you a link to the challenge and to the write-up with the solution. I highly recommend looking at it. It's a nice way to have this practical understanding of how the security of the batch opening can depend on the random variables that we discussed today. And obviously, like, any questions are welcome. So if there are any questions, feel free to ask. The slides for this presentation will be posted on Dōjō Hacker Forum. And yeah, if there are any questions, I would love to address them. Okay, no questions so far. Feel free to reach out to the Dora Hacks forum of the Dōjō Hacker and ask any questions. I would love to help you out if you have any questions. And yep, probably then we are done for today. Thanks for coming. I hope that you got some insights into how KZG commitment scheme works, and hope to see you again in the future on the new workshops by the Dōjō Hacker. Thanks everyone. Have a nice day, guys. Bye-bye.